The universe contains somewhere in the vicinity of 2 trillion galaxies, a number that itself represents a significant upward revision from earlier estimates that placed the count closer to 200 billion. That revision, published in 2016 by a team led by Christopher Consellis at the University of Nottingham, emerged not from a single dramatic observation, but from a painstaking statistical analysis that accounted for galaxies too faint and too distant to appear in even the deepest images taken by the Hubble Space Telescope. The implication was that roughly 90% of all galaxies in the observable universe had never been directly seen, and that our understanding of galactic populations was built on a sample that, however impressive in absolute terms, represented only a sliver of the total. Within that enormous population, most galaxies are relatively unremarkable by the standards of astrophysics. They form stars at moderate rates, contain black holes of moderate mass, span moderate distances, and evolve on timescales that, while immense by human reckoning, are ordinary by cosmic standards. But at the tails of every distribution, there exist objects that push against the boundaries of what physical models predict. Objects so luminous, so massive, so prolific in star formation, so ancient, so empty, or so structurally peculiar that their very existence forces revisions to theory. These are the galaxies that occupy the subject of this discussion, and examining them in detail reveals not merely a catalogue of cosmic superlatives, but a deeper picture of how galaxies form, grow, interact, and sometimes defy the expectations that decades of careful modeling have established. To appreciate what makes a galaxy extreme, it helps to establish what counts as typical. The Milky Way, the galaxy in which our solar system resides, is a barred spiral galaxy with a stellar mass of roughly 50 to 60 billion solar masses, a disk diameter of about 100,000 light-years, a central supermassive black hole of approximately 4 million solar masses, and a star formation rate of roughly 1 to 2 solar masses per year. These numbers place it squarely in the middle of the distribution for large spiral galaxies, neither especially massive nor especially small, neither especially active nor especially quiescent. Its neighbor, the Andromeda Galaxy, is somewhat larger and more massive, with a stellar mass closer to 100 billion solar masses and a slightly lower current star formation rate. But it too falls well within the range of normal large spirals. Most galaxies in the local universe are considerably smaller than either of these, with dwarf galaxies outnumbering large ones by perhaps a factor of 10 or more, a fact that has important consequences for hierarchical models of galaxy formation in which large structures are built up over time through the merger of smaller ones. Against this backdrop, the first category of extremity worth examining involves sheer physical size. The largest galaxies known are not spirals, but giant ellipticals, typically found at the centers of massive galaxy clusters, where they have grown over billions of years by cannibalizing smaller galaxies that fall into the cluster's gravitational well. The most commonly cited example is IC 1101, located at the center of the Abell 2029 galaxy cluster, roughly 1 billion light-years from Earth. IC 1101 has been variously estimated to span somewhere between 2 million and 6 million light-years in diameter, depending on how one defines the boundary of such a diffuse object and which wavelength of light is used to measure it. Its stellar mass has been estimated at roughly 100 trillion solar masses, placing it among the most massive galaxies known by any measure. The uncertainty in these numbers is itself instructive, because giant elliptical galaxies do not have sharp edges. Their stellar density drops off gradually with distance from the center, following what is known as a Cercic profile, and at some point the outermost stars become indistinguishable from the intracluster light, a diffuse glow of stars that have been stripped from their parent galaxies and now orbit freely within the cluster potential. Whether those stripped stars should be counted as part of IC 1101 or as a separate population is partly a matter of definition, and different definitions yield different size estimates. The process by which galaxies like IC 1101 attain such enormous sizes is known as galactic cannibalism, a term coined by the astronomer J. Tonry in the late 1970s, though the basic idea had been discussed earlier by Jeremiah Ostraker and others. In a galaxy cluster, the most massive galaxy tends to sink toward the center of the cluster's gravitational potential through a process called dynamical friction, in which the gravitational pull of surrounding matter creates a wake behind the moving galaxy that decelerates it. Once at the center, this brightest cluster galaxy, as it is known in the literature, encounters a steady stream of smaller galaxies falling inward, and it grows by absorbing them. Simulations show that this process can account for a significant fraction of the final mass of the central galaxy, with some models suggesting that as much as half of the stellar mass of the most massive, brightest cluster galaxies was accreted from other galaxies rather than formed in situ. This has observational consequences. The stars in giant ellipticals tend to be old, red, and metal-rich, consistent with a population that formed early and has not experienced significant new star formation in many billions of years. The velocity dispersions of their stars are high, reflecting the deep gravitational potential wells in which they sit, and their light profiles tend to be smooth and featureless, lacking the spiral arms, dust lanes, and star-forming regions that characterize galaxies still actively converting gas into stars. But IC 1101, while often cited as the largest galaxy, may not actually hold that record in every meaningful sense. A galaxy catalogued as Alcyonius, discovered in 2022 by Martijn Oey and colleagues using the Low-Frequency Array Radio Telescope, or LOFAR, extends approximately 16 million light-years from end to end when its radio lobes are included. Alcyonius is a giant radio galaxy, a type of active galaxy in which jets of plasma launched by the central supermassive black hole extend far beyond the visible boundaries of the host galaxy and inflate enormous lobes of radio-emitting plasma in the intergalactic medium. The host galaxy of Alcyonius is itself not especially remarkable in optical terms, with a stellar mass of roughly 240 billion solar masses, large but not extraordinarily so. What makes Alcyonius extreme is the extent of its radio structure, which dwarfs anything produced by its stellar population. The jets that created these lobes were powered by accretion of matter onto the central black hole, and the fact that they reached such enormous distances suggests that the intergalactic medium in the vicinity of Alcyonius is unusually low in density, offering less resistance to the expanding plasma. This connection between the properties of a galaxy's active nucleus and the environment in which it is embedded illustrates a broader theme in extragalactic astronomy, namely that no galaxy can be understood in isolation from its surroundings. At the opposite end of the size spectrum lie galaxies so small and faint that they were unknown until relatively recently. Ultra-faint dwarf galaxies, most of them satellites of the Milky Way or the Andromeda Galaxy, contain as few as a few thousand stars and have luminosities less than 1,000th that of the Milky Way. The faintest known as of the early 2020s include objects like Segway 1, which contains only about 1,000 stars within a half-light radius of roughly 30 parsecs, and Tucana II, whose total luminosity is on the order of 300 solar luminosities. These objects are extreme not in their brightness or mass, but in their darkness. Their stellar masses are tiny, but their dynamical masses, inferred from the velocities of their stars, suggest that they are embedded in dark matter halos many times more massive than their visible components would indicate. In Segway 1, for instance, the mass-to-light ratio has been estimated at roughly 3,400 in solar units, meaning that for every unit of light the galaxy produces, it contains more than 3,000 times as much mass as the Sun would need to produce that much light. This places Segway 1 among the most dark matter-dominated objects known in the universe, and studying such galaxies provides one of the most direct empirical constraints on the properties of dark matter, including its spatial distribution on small scales and its minimum halo mass. The existence of ultra-faint dwarfs also bears on a long-standing discrepancy in cosmology known as the missing satellites problem. Standard cold dark matter simulations predict that a Milky Way mass halo should contain thousands of smaller subhalos, each potentially hosting a dwarf galaxy, but until the mid-2000s only a few dozen satellite galaxies of the Milky Way were known. The discovery of ultra-faint dwarfs, beginning with the Sloan Digital Sky Survey and continuing with the Dark Energy Survey and other programs, has partially closed this gap. But the question of whether the remaining discrepancy reflects a genuine physical suppression of galaxy formation in small halos, an observational incompleteness in our surveys, or a problem with the cold dark matter model itself remains a subject of active research. Some models invoke the ionizing radiation of the early universe, which would have heated gas in small halos and prevented it from cooling and forming stars, as a mechanism for producing dark subhalos that contain no visible galaxy at all. Others suggest that feedback from supernovae in the first generation of stars could have expelled gas from small halos and truncated star formation. The ultra-faint dwarfs that we do observe may represent a transition population, halos that were just barely massive enough to retain some gas and form a small number of stars before one of these suppression mechanisms shut them down. Turning from size and mass to luminosity, the most luminous galaxies in the universe are not the giant ellipticals, despite their enormous stellar populations, but rather galaxies whose luminosity is dominated by processes other than ordinary starlight. The most extreme examples are quasars, a term derived from quasi-stellar radio source, and coined in the 1960s when these objects were first identified as distant galaxies harboring extraordinarily luminous active nuclei. The most luminous quasar known as of recent measurements is a source sometimes designated SMSS J20 712ER Timon 136 5.1, though the record changes as new surveys probe deeper and wider areas of the sky. Its luminosity has been estimated at roughly 500 trillion times the luminosity of the Sun, or equivalently about 500 times the luminosity of the entire Milky Way, and this energy emerges not from a population of hundreds of billions of stars, but from a region smaller than our solar system, surrounding a supermassive black hole of roughly 17 billion solar masses. The energy source is gravitational, specifically the conversion of gravitational potential energy into radiation, as matter spirals inward through an accretion disk, and the efficiency of this process, typically around 10% by mass energy equivalence, far exceeds the roughly 0.7% efficiency of nuclear fusion in stellar cores. This is why a single accreting black hole can outshine an entire galaxy. But the luminosity of quasars, while impressive, raises its own set of questions when the most distant and therefore earliest examples are considered. The discovery of luminous quasars at redshifts above 7, corresponding to a time when the universe was less than about 800 million years old, implies that supermassive black holes of 1 billion solar masses or more had already assembled by that epoch. This is difficult to explain with standard models of black hole growth, in which a stellar mass seed black hole, formed by the collapse of a massive star, grows by accreting gas at rates limited by radiation pressure, a constraint known as the Eddington limit. A black hole accreting at the Eddington rate doubles its mass on a timescale of roughly 45 million years, and even continuous Eddington rate accretion from a seed of a few tens of solar masses would require more time than was available in the first 800 million years to produce a billion solar mass black hole. Several solutions have been proposed. One is that the seed black holes were much more massive than stellar remnants, perhaps forming through the direct collapse of massive gas clouds in primordial halos that had not yet been enriched with metals, a mechanism that could produce seeds of 10,000 to 100,000 solar masses. Another is that accretion occasionally exceeded the Eddington rate, a possibility supported by some theoretical models and simulations that show how photon trapping in dense accretion flows can reduce the effective radiation pressure and allow super-Eddington accretion to occur. A third possibility involves mergers of black holes in the dense environments of the early universe, though this requires efficient orbital decay mechanisms to bring black hole pairs together on the necessary timescales. The James Webb Space Telescope, launched in December 2021 and operational from mid-2022, has begun to provide new data on the properties of galaxies and black holes at very high redshifts, and some of its earliest results have complicated the picture further by revealing galaxies that appear more massive, more luminous, and more mature than expected at such early times. Among the most discussed early results from the James Webb Space Telescope are observations of galaxies at redshifts of 10 and above, corresponding to the first few hundred million years after the Big Bang, that appear to have stellar masses of several billion solar masses. If confirmed, these objects would be difficult to accommodate within standard models of galaxy formation, which predict that such massive galaxies should not have had time to assemble by those epochs. The key uncertainty lies in the interpretation of the photometric data. At very high redshifts, the spectral energy distributions of galaxies are shifted into the infrared, and estimating stellar masses from broadband photometry requires assumptions about the stellar initial mass function, the star formation history, the metallicity, and the contribution of nebula emission lines to the observed fluxes. Different assumptions can yield stellar mass estimates that differ by factors of several, and some early claims of impossibly massive high redshift galaxies have been revised downward as spectroscopic confirmations have become available and as more sophisticated modeling has been applied. Nevertheless, even the revised estimates suggest that galaxy formation in the early universe may have been more efficient than previously thought, and that feedback mechanisms, which in standard models regulate star formation by heating and expelling gas, may have been less effective in the first few 100 million years. This is an area of rapid development, and the tension between observations and models is likely to evolve significantly as more data become available. A different kind of luminosity extreme is represented by a class of objects known as ultraluminous infrared galaxies, or ULIRGs, which emit the bulk of their energy in the far infrared part of the spectrum. The prototype of this class is ARP 220, located about 250 million light-years from Earth, which has a total infrared luminosity of approximately 1 trillion solar luminosities. The energy source in ULIRGs is a combination of intense star formation and, in many cases, an obscured active galactic nucleus, with the optical and ultraviolet light from these sources absorbed by surrounding dust and re-emitted at infrared wavelengths. The dust acts as a calorimeter, capturing essentially all of the short wavelength radiation and converting it to thermal emission at longer wavelengths. And this is why ULIRGs are so bright in the infrared while being relatively faint in the optical. Most ULIRGs are found to be ongoing mergers of gas-rich galaxies, in which the collision has funneled large quantities of gas toward the center, triggering an intense burst of star formation, a phenomenon often referred to as a starburst, and possibly also feeding the central black hole. ARP 220 itself shows clear morphological signs of a recent major merger, with two distinct nuclei separated by roughly 300 parsecs, each containing a compact source of emission that may be a heavily obscured active nucleus or an exceptionally dense star-forming region or both. The most extreme starbursts bring us to another category of galactic extremity, that of star formation rate. In the Milky Way, as noted, roughly 1 to 2 solar masses of gas are converted into stars each year. In a typical ULIRG, this rate rises to several hundred solar masses per year. But in the most extreme starburst galaxies known, the rate can exceed 1,000 solar masses per year, or even approach 10,000. A notable example is SPT 034652, a dusty star-forming galaxy at a redshift of approximately 5.7, corresponding to a look-back time of about 12.5 billion years, which was discovered through its thermal dust emission by the South Pole Telescope and subsequently observed at multiple wavelengths. Its star formation rate has been estimated at roughly 4,500 solar masses per year, making it one of the most intensely star-forming galaxies ever identified at any epoch. This rate is so high that if sustained, it would exhaust the galaxy's available gas supply in a few tens of millions of years, a timescale that is short even by the standards of galaxy evolution. Such extreme starbursts are thought to represent brief, transient phases in a galaxy's history, typically triggered by major mergers or by rapid gas accretion from the intergalactic medium, and they are believed to play a role in the formation of the most massive elliptical galaxies seen in the local universe, which may be the quenched descendants of these earlier episodes of prodigious star formation. The connection between starbursts and the subsequent quenching of star formation is itself an area of considerable complexity. Quenching refers to the cessation of star formation in a galaxy, and it is observed that the most massive galaxies in the local universe, the giant ellipticals and brightest cluster galaxies discussed earlier, have essentially no ongoing star formation and have not formed significant numbers of new stars in many billions of years. How they arrived at this state is debated, but most models invoke some combination of two mechanisms. The first is stellar feedback, in which energy and momentum deposited by supernovae, stellar winds, and radiation pressure from massive stars heat and eject gas from the star-forming regions, reducing the available fuel for further star formation. The second is active galactic nucleus feedback, in which energy from the central supermassive black hole, delivered either through radiation during a quasar phase or through mechanical energy in the form of jets during a radio mode phase, heats the surrounding gas to temperatures at which it cannot cool and collapse to form new stars. The relative importance of these mechanisms, their dependence on galaxy mass and environment, and the timescales over which they operate are all subjects of ongoing investigation, and different models make different predictions about the observable properties of galaxies in the process of quenching. Predictions that can in principle be tested against observations of galaxies caught in the act of transitioning from star-forming to quiescent. A particularly striking category of quenched galaxies is the class of objects sometimes referred to as red and dead galaxies at high redshift. Galaxies that appear to have completed their star formation and become quiescent at surprisingly early times. The most extreme known examples include galaxies at redshifts of 3 to 4, corresponding to look-back times of roughly 11 to 12 billion years, that already have stellar masses of several hundred billion solar masses and no detectable ongoing star formation. The existence of such massive quiescent galaxies at these early epochs places tight constraints on the timeline of galaxy formation and quenching, because it implies that these galaxies must have formed the bulk of their stars even earlier, perhaps at redshifts of 5 to 8, in intense bursts lasting a few hundred million years, and then shut down star formation rapidly. The mechanism for this rapid quenching is not well understood. Some models propose that a burst of black hole activity following a major merger can heat and expel the remaining gas on short timescales, while others suggest that the very intensity of the starburst itself may be self-limiting, with the energy released by a large population of massive stars sufficient to unbind the gas reservoir. A further complication is that these massive quiescent galaxies at high redshift tend to be very compact, with half-light radii of only 1 or 2 kiloparsecs, roughly 5 to 10 times smaller than equally massive elliptical galaxies in the local universe. This means that they have grown significantly in size between then and now, a process known as size evolution, which is thought to occur primarily through minor mergers, the accretion of many small galaxies that add stars to the outskirts without significantly increasing the total stellar mass, but substantially increasing the physical extent of the galaxy. Among the most extreme objects identified by the James Webb Space Telescope in its first years of operation are galaxies that challenge these formation timelines even further. One such object, designated JD's GS Z14-0, was confirmed through spectroscopy at a redshift of approximately 14.2, placing it at a time when the universe was only about 300 million years old. Its ultraviolet luminosity and inferred star formation rate suggest that it had already built up a significant stellar population by that epoch, and its relatively large apparent size, extended over more than 1,000 light-years in its rest frame ultraviolet emission, argues against it being a purely point-like active nucleus and supports the interpretation that its luminosity is indeed powered primarily by stars. Finding galaxies this luminous this early was not anticipated by most pre-launch predictions, and while individual objects can always be attributed to rare upward fluctuations in the underlying density field, the cumulative number of unexpectedly luminous galaxies at redshifts above 10 has prompted re-examinations of the assumptions built into galaxy formation models, including the efficiency of star formation in early halos, the role of dust attenuation at high redshift, and the possibility that the stellar initial mass function in the early universe differed from the one observed locally, perhaps being weighted more heavily toward massive stars that produce more light per unit mass formed. The stellar initial mass function, often abbreviated as the IMF, is one of the most fundamental yet poorly constrained inputs to models of galaxy evolution. It describes the distribution of stellar masses produced in a given episode of star formation and is usually parameterized as a power law or a broken power law, with the most commonly used formulations being those of Edwin Salpeter, published in 1955, and the somewhat flatter versions proposed by Pavel Krupa in 2001 and by Gilles Chabrier in 2003. The Salpeter IMF predicts a relatively larger fraction of massive stars compared to the Krupa and Chabrier versions, and the choice of IMF directly affects the inferred stellar masses and star formation rates of observed galaxies, because massive stars contribute disproportionately to the total luminosity even though they represent a small fraction of the total stellar mass. If the IMF in the early universe were systematically different from the local one, for example, if it were more top-heavy, favoring more massive stars, then the same observed luminosity would correspond to a smaller total stellar mass, potentially alleviating the tension between observations of early luminous galaxies and model predictions. There is some theoretical motivation for such a change, since the characteristic mass of collapsing gas clouds depends on the temperature and composition of the gas, and at very low metallicities, the reduced cooling efficiency might lead to higher characteristic masses. However, direct observational evidence for IMF variations remains limited and contested, and the question of whether the IMF is truly universal or varies with environment and epoch is one of the major open problems in stellar and galactic astrophysics. Returning to the theme of extreme luminosity, another important class of objects is the submillimeter galaxies, often abbreviated as SMGs, which were first identified in large numbers by the Submillimeter Common User Bolometer Array, or SCUBA, on the James Clerk Maxwell Telescope in the late 1990s. These galaxies emit the bulk of their energy at wavelengths around 850 micrometers, deep in the submillimeter portion of the electromagnetic spectrum, and they are among the most luminous objects in the universe at these wavelengths. Their infrared luminosities typically exceed 10 to the 13 solar luminosities, placing them in the hyperluminous infrared galaxy category, and their star formation rates are correspondingly extreme, often exceeding 1,000 solar masses per year. Most SMGs are found at redshifts of 2 to 3, the epoch often referred to as cosmic noon, because it corresponds to the peak of the cosmic star formation rate density, and they are thought to represent the most vigorous star-forming systems of that era. Their space density, however, is very low, and they contribute only a small fraction of the total star formation at those epochs, with the bulk being contributed by more numerous but less luminous galaxies. The relationship between SMGs and other galaxy populations is a subject of ongoing study, with some evidence suggesting that SMGs evolve into the massive quiescent galaxies seen at slightly later epochs, consistent with a picture in which the most massive galaxies form their stars early and rapidly in intense bursts and then quench. A related class of extreme objects is the so-called hot dust-obscured galaxies, or hot dogs, identified by the Wide Field Infrared Survey Explorer, or WISE, satellite. These are among the most luminous galaxies in the infrared, with bolometric luminosities reaching 10 to the 14 solar luminosities, or 100 trillion times the luminosity of the Sun. Unlike typical ULIRGs or SMGs, whose infrared emission peaks at relatively long wavelengths, corresponding to cold dust temperatures of 30 to 50 Kelvin, the spectral energy distributions of hot dogs peak at shorter wavelengths, indicating dust temperatures of 60 Kelvin or higher. This high dust temperature is thought to arise because the dominant heating source is not star formation, but an extremely luminous active galactic nucleus, whose intense radiation heats the surrounding dust to higher temperatures than starlight alone could achieve. The most luminous hot dog known, WISE J2460 57 052635.0, has an estimated bolometric luminosity of approximately 300 trillion solar luminosities, making it one of the most luminous persistent objects ever identified. Its central black hole has been estimated at several billion solar masses, and the high luminosity implies that it may be accreting at or somewhat above the Eddington rate. The environment of this galaxy shows evidence of companion galaxies, suggesting that it may reside in a protocluster, a region destined to evolve into a massive galaxy cluster by the present day. The mention of protoclusters raises another dimension of galactic extremity, that of environment. Galaxies do not exist in isolation, but are distributed in a cosmic web of filaments, sheets, and nodes, with the densest concentrations found in galaxy clusters. The most massive galaxy clusters in the local universe, such as the Coma cluster and the Virgo cluster, contain hundreds or thousands of galaxies within a volume a few megaparsecs across, and the total mass of such clusters, including dark matter, reaches 10 to the 15 solar masses or more. At higher redshifts, the progenitors of these clusters, the protoclusters, are observed as overdense regions containing enhanced numbers of galaxies and elevated rates of star formation and black hole accretion. One of the most extreme protoclusters known is SPT 234956, at a redshift of approximately 4.3, which contains at least 14 sub-millimeter bright galaxies within a region only about 130 kiloparsecs in diameter, all apparently in the process of merging. The total star formation rate within this system exceeds 6,000 solar masses per year, and simulations suggest that these galaxies will merge into a single massive galaxy within a few 100 million years, producing an object comparable to the brightest cluster galaxies seen at lower redshifts. The discovery of such dense, actively merging systems at high redshift provides direct evidence for the hierarchical assembly process by which the most massive structures in the universe are built. A qualitatively different kind of extreme is represented by galaxies with anomalously low or high dark matter content. In the standard cosmological model, every galaxy is embedded in a dark matter halo, and the mass of the halo typically exceeds the mass of the visible, baryonic component by a factor of 5 to 10 or more. However, in 2018, Peter van Dokkum and colleagues reported the discovery of a galaxy designated NGC 1052 DF2, an ultra-diffuse galaxy in the vicinity of the elliptical galaxy NGC 1052 that appeared to have little or no dark matter. Their analysis, based on the velocities of 10 globular clusters associated with the galaxy, yielded a total mass consistent with the stellar mass alone, with no significant dark matter component required. This result, if correct, was paradoxical in two ways. First, it challenged the expectation that all galaxies form within dark matter halos. Second, it actually provided evidence against modified gravity theories, such as modified Newtonian dynamics, or MOND, which predict that the apparent effect of dark matter is inseparable from the presence of baryonic matter and therefore cannot be absent from a galaxy that contains stars. In MOND, any collection of matter should exhibit the enhanced gravitational effects attributed to dark matter, so a galaxy without dark matter is straightforward to explain in the standard model, where dark matter is a separate substance that can in principle be separated from baryonic matter through tidal interactions, but difficult to explain in MOND. A second similar galaxy, NGC 1052 DF4, was subsequently reported by the same group. The results were debated, with some independent analyses finding higher velocity dispersions for the globular clusters and therefore higher inferred total masses. But the basic claim has withstood scrutiny to the degree that these galaxies are now widely considered to have anomalously low dark matter fractions. One proposed formation mechanism involves tidal stripping during a close encounter with the massive galaxy NGC 1052, in which the dark matter halo, being more extended and less centrally concentrated than the stellar component, is preferentially removed. At the other extreme, there exist galaxies that appear to be almost entirely dark matter, with only a tiny fraction of baryonic material. Dragonfly 44, another ultra-diffuse galaxy, this one located in the Coma cluster, was reported in 2016 by Van Dokkum and colleagues to have a total mass of roughly 1 trillion solar masses, but a stellar mass of only about 300 million solar masses, giving it a mass-to-light ratio of approximately 98% dark matter. This made it comparable in total mass to the Milky Way, but with roughly 1/100th of the stars. Subsequent analyses have debated the exact dark matter fraction, with some studies finding lower total masses, but even the more conservative estimates place Dragonfly 44 among the most dark matter-dominated large galaxies known. Ultra-diffuse galaxies in general have attracted considerable attention since their recognition as a distinct population in the mid-2010s, thanks in large part to observations with the Dragonfly telephoto array, a custom-built instrument optimized for detecting low-surface brightness features. These galaxies have stellar masses comparable to dwarf galaxies, but physical extents comparable to the Milky Way, giving them extremely low surface brightnesses that make them difficult to detect with conventional telescopes. They are found in a variety of environments, from dense galaxy clusters to the field, and their formation mechanisms remain debated. Possible explanations include failed Milky Way-type galaxies that lost their gas before forming many stars, dwarf galaxies that were puffed up by tidal interactions or internal feedback, or the products of gas-rich mergers at high redshift. The topic of dark matter content connects to one of the most profound questions in extragalactic astronomy, namely the relationship between galaxies and their dark matter halos. This relationship is often described in terms of the stellar mass-halo mass relation, which quantifies the average stellar mass of a galaxy as a function of the mass of its host dark matter halo. This relation is not a simple proportionality. At low halo masses, the efficiency of converting baryons into stars is very low, presumably because feedback from supernovae and photoionization heating expel gas and prevent further star formation. At high halo masses, the efficiency also drops, perhaps because active galactic nucleus feedback prevents cooling of the hot gas in massive halos. The peak efficiency occurs at halo masses of around 10 to the 12 solar masses, roughly the mass of the Milky Way's halo, where approximately 20 to 30% of the available baryons have been converted into stars. Galaxies at the extremes of the stellar mass-halo mass relation, those with anomalously high or low star formation efficiencies for their halo mass, represent important tests of these feedback models, and identifying and characterizing such outliers is an active area of research. Another dimension of extremity involves the properties of the central supermassive black holes found in most, if not all, massive galaxies. The most massive black holes known have masses exceeding 10 billion solar masses. The black hole at the center of the galaxy M87, famously imaged by the Event Horizon Telescope collaboration in 2019, has a mass of approximately 6.5 billion solar masses. But this is not the most massive known. The black hole in NGC 4889, the brightest galaxy in the Coma cluster, has been estimated at roughly 21 billion solar masses, based on the velocity dispersion of stars in its vicinity, though the uncertainty on this measurement is large, spanning roughly a factor of 2. The black hole in the galaxy, Holm 15A, the central galaxy of the Abell 85 cluster, has been estimated at approximately 40 billion solar masses, potentially making it one of the most massive black holes ever measured. These extreme black hole masses raise questions about how such objects grew so large. In the local universe, the mass of the central black hole is observed to correlate tightly with several properties of the host galaxy, including the velocity dispersion of the bulge, the mass of the bulge, and the luminosity of the bulge, relationships known as the M-sigma relation and related scaling laws. These correlations suggest a co-evolutionary process in which the growth of the black hole and the growth of the galaxy are somehow regulated by a common mechanism, likely involving feedback from the active nucleus. But the details of this co-evolution are not fully understood, particularly at the most massive end, where the black holes are so enormous that their gravitational spheres of influence encompass thousands of light-years. The phenomenon of gravitational lensing provides another way in which galaxies can exhibit extreme properties, specifically extreme magnification. When a massive galaxy or galaxy cluster lies along the line of sight to a more distant galaxy, the gravitational field of the foreground object can bend and focus the light of the background object, producing multiple images, arcs, or rings, and amplifying its apparent brightness by factors that can range from a few to several thousand. The most extremely magnified individual stars ever observed were detected through such lensing configurations. A star nicknamed Earendel, formerly designated WHL 0137 LS, was discovered in a highly magnified arc behind the galaxy cluster WHL 0137 08, at a redshift of 6.2, corresponding to a time when the universe was roughly 900 million years old. Its magnification was estimated at a factor of thousands, resulting from its fortuitous position very close to the critical curve of the lens, a line of theoretically infinite magnification. Without this extreme lensing, the star would have been far too faint to detect with any existing telescope. While Earendel is a single star rather than a galaxy, its detection illustrates how gravitational lensing can turn foreground galaxy clusters into cosmic telescopes that reveal objects that would otherwise lie far beyond our observational reach, and several of the most detailed studies of early galaxies have relied on such lensing magnification to achieve the sensitivity and spatial resolution needed to resolve their internal structure. The structure of galaxies themselves can also be extreme in ways that go beyond simple measures of size, mass, or luminosity. Ring galaxies, for instance, are rare and structurally unusual objects in which a ring of stars and gas surrounds a relatively empty interior. The best-known example is Hoag's object, discovered by Arthur Hoag in 1950, which consists of a nearly perfect ring of blue young stars surrounding an older yellow core, with a gap between the two that is largely devoid of visible stars. The formation mechanism for Hoag's object remains debated, with proposals including a past collision with another galaxy that passed through the center of the disk, triggering an expanding wave of star formation and the accretion of a gas-rich companion whose material settled into a ring. Other ring galaxies, such as the Cartwheel Galaxy, have more clearly established formation histories involving collisional interactions, and the James Webb Space Telescope's infrared images of the Cartwheel Galaxy, released in 2022, revealed previously hidden details of its star formation activity and dust distribution that shed new light on the propagation of the star-forming wave through its disk. Polar ring galaxies represent another structural peculiarity in which a ring of gas, dust, and stars orbits in a plane roughly perpendicular to the main disk of the galaxy. The best-studied example is NGC 4654a, in which a thin disk galaxy is surrounded by a ring of material orbiting at roughly 90 degrees to the disk plane. These systems are thought to form through the accretion of material from a companion galaxy or from the intergalactic medium, with the accreted material settling into an orbit that is misaligned with the existing disk. Polar ring galaxies are scientifically valuable because they allow the shape of the dark matter halo to be probed in two perpendicular planes, providing information about whether the halo is spherical, oblate, or prolate, a measurement that is otherwise very difficult to make. Jellyfish galaxies represent still another form of structural extremity. These are galaxies falling into galaxy clusters that are experiencing ram pressure stripping, a process in which the hot intra-cluster medium exerts a pressure on the galaxy's interstellar gas as it moves through the cluster, displacing the gas from the galaxy's disk and creating long trailing tails of stripped material that can extend for tens of kiloparsecs behind the galaxy, giving it a visual appearance reminiscent of a jellyfish. The most extreme examples show nearly complete removal of the galaxy's gas, effectively quenching its star formation by removing the raw material from which new stars would form. Paradoxically, the ram pressure can also trigger enhanced star formation in the compressed leading edge of the gas disk, and even in the stripped tails themselves, where dense clumps of displaced gas collapse and form stars in the intergalactic medium. The GASP survey, or GIAS stripping phenomena in galaxies, led by Bianca Poggianti and colleagues, has systematically studied jellyfish galaxies in the nearby universe, finding that many of them host active galactic nuclei at rates higher than expected for galaxies of similar mass, suggesting that the ram pressure may also funnel gas toward the central black hole and trigger nuclear activity. Moving to another form of extremity, some galaxies exhibit extreme chemical compositions. The metallicity of a galaxy, defined in astrophysics as the abundance of elements heavier than helium relative to hydrogen, typically correlates with its stellar mass, a relationship known as the mass-metallicity relation. More massive galaxies tend to have higher metallicities because they have deeper gravitational potential wells that retain the metals produced by supernovae, while lower-mass galaxies tend to lose metals through supernova-driven outflows. At the extreme low end of the metallicity distribution are galaxies like I Zwicky 18, which for many years was considered the most metal-poor galaxy known, with an oxygen abundance roughly 1/50th of the solar value. It was initially suggested that I Zwicky 18 might be a genuinely young galaxy, forming its first stars in the present epoch, but deeper observations revealed an underlying population of older red giant branch stars, indicating that it had been forming stars, albeit at a very low rate, for billions of years. More recently, galaxies with even lower metallicities have been identified, including objects found in the Sloan Digital Sky Survey and in targeted searches for extremely metal-poor systems, with some reaching oxygen abundances of roughly 1/100th of the solar value or even lower. At the high metallicity end, the central regions of some massive elliptical galaxies exhibit supersolar metallicities, with iron abundances 2 to 3 times the solar value, reflecting the intense and prolonged star formation histories of these systems and the efficient retention of metals in their deep potential wells. The chemical composition of galaxies is not only about average metallicity, but also about the relative abundances of different elements, which carry information about the nucleosynthetic processes and timescales that produced them. The ratio of alpha elements such as oxygen, magnesium, silicon, and calcium, which are primarily produced by core collapse supernovae from massive stars, to iron peak elements, which are produced in larger quantities by type Ia supernovae from white dwarf progenitors with longer delay times, is particularly informative. Massive elliptical galaxies tend to have enhanced alpha to iron ratios, indicating that their star formation occurred rapidly enough to be enriched primarily by core collapse supernovae before the longer delay type Ia supernovae could contribute significant amounts of iron. This alpha enhancement is one of the strongest pieces of evidence that these galaxies formed their stars in short, intense bursts, rather than in prolonged, steady episodes. At the most extreme, the alpha enhancement factors reach values of 0.3 to 0.5 dex above the solar ratio, corresponding to star formation timescales of only a few 100 million years. Some of the most extreme galaxies, in terms of their observable properties, are those undergoing interactions or mergers. While the merger rate in the local universe is relatively low, mergers were more common at earlier epochs, and the most violent examples produced dramatic morphological disturbances, tidal tails extending for hundreds of kiloparsecs, bridges of material connecting the interacting galaxies, and shells and ripples in the stellar distribution that can persist for billions of years after the merger is complete. The antennae galaxies, NGC 4038 and NGC 4039, at a distance of roughly 65 million light-years, are among the best-studied ongoing major mergers in the nearby universe. Their long tidal tails, extending over 300 kiloparsecs, contain dense concentrations of gas and young star clusters, and the overlap region between the two galaxies is the site of some of the most intense star formation in the local universe, with star formation rates per unit area that exceed those in any region of the Milky Way by orders of magnitude. The antennae system also contains a population of several thousand young massive star clusters, some of which may evolve into objects resembling the globular clusters found in the halos of mature galaxies, suggesting that globular cluster formation is associated with the extreme conditions of major mergers. The study of galaxy mergers has been greatly aided by numerical simulations, which can follow the evolution of interacting galaxies over hundreds of millions of years and predict the observable properties of the merger remnants. A pioneering series of simulations by Allard and Jury Toumre in 1972 demonstrated that many of the morphological peculiarities observed in interacting galaxies, including tidal tails, bridges, and asymmetries, could be reproduced by the gravitational interaction of two disk galaxies, without the need to invoke any exotic physics. More recent simulations incorporate gas dynamics, star formation, black hole growth, and feedback processes, and they have shown that the outcome of a merger depends sensitively on the mass ratio of the galaxies, the gas fractions, the relative orientations of the disks, and the orbital parameters of the encounter. Major mergers between roughly equal mass gas-rich disk galaxies are predicted to produce remnants that resemble elliptical galaxies, a result known as the merger hypothesis for elliptical galaxy formation, originally proposed by Toumre in 1977. Minor mergers in which a small galaxy is accreted by a much larger one are predicted to thicken the disk and add material to the stellar halo without fundamentally transforming the morphology, and the stellar halos of massive galaxies are expected to be built largely through such minor accretion events. The fossil record of past mergers can be read in the stellar halos of nearby galaxies, where the accreted material forms streams, shells, and diffuse envelopes of low surface brightness that can persist for many giga-years. The Stellar Streams Legacy Survey and similar programs have revealed a rich structure of such debris around the Milky Way and other nearby galaxies, with individual streams tracing the orbits of long-disrupted dwarf galaxies. The Sagittarius Dwarf Elliptical Galaxy, discovered in 1994, is currently being tidally disrupted by the Milky Way and has produced a stream of stars that wraps at least once around the galaxy. The Magellanic Stream, a long filament of gas stretching more than 100 degrees across the sky, traces the interaction between the large and small Magellanic Clouds and the Milky Way, and provides evidence for the complex orbital history of these satellite galaxies. An entirely different form of galactic extremity is represented by active galaxies, whose emission is dominated by relativistic jets pointed close to the line of sight toward the observer. These objects, known as blazars, exhibit the most extreme variability, the highest apparent luminosities, and the most energetic photon emission of any class of active galaxies. The apparent luminosity of a blazar can exceed the intrinsic luminosity of the jet by a large factor due to relativistic beaming. The combined effects of time dilation, aberration, and Doppler shifting that concentrate the jet's emission into a narrow cone along its direction of motion. When this cone happens to point toward Earth, the observed flux is dramatically enhanced. Markarian 421 and Markarian 501 are among the best-studied nearby blazars, and they have been detected at photon energies exceeding 1 tera-electron-volt, corresponding to individual photons more than 1 trillion times more energetic than those of visible light. The physical processes responsible for accelerating particles to such extreme energies within the jet are not fully understood, but are thought to involve shock acceleration, magnetic reconnection, or turbulent acceleration in the magnetized plasma of the jet. Blazars are also of interest as sources of astrophysical neutrinos, with the IceCube Neutrino Observatory having reported in 2018 a high-energy neutrino event spatially and temporally coincident with a flaring blazar, TXS 0506 plus 0056, providing the first strong evidence for the association of high-energy neutrinos with an identifiable extragalactic source and opening the era of multi-messenger astronomy involving galaxies. The phenomenon of galactic-scale outflows represents another manifestation of extreme activity. In many active and star-forming galaxies, observations reveal high-velocity flows of gas being expelled from the galaxy at speeds of hundreds to thousands of kilometers per second. These outflows can be driven by the combined energy of supernovae in a starburst, by radiation pressure from an active galactic nucleus, or by the mechanical energy of jets. In some cases, the outflow rates exceed the star formation rates, meaning that the galaxy is expelling gas faster than it is converting gas into stars, a condition that, if sustained, would rapidly deplete the galaxy's gas reservoir and quench star formation. Molecular outflows, detected through observations of carbon monoxide and other molecular traces, are of particular interest because they involve the cold, dense gas from which stars actually form, rather than the hot, diffuse gas that constitutes most of the volume of the outflow. The galaxy Markarian 231, the nearest quasar-host galaxy at a distance of roughly 600 million light-years, exhibits a molecular outflow with a mass outflow rate of approximately 700 solar masses per year, comparable to its star formation rate of roughly 200 solar masses per year, suggesting that the outflow is in the process of depleting the galaxy's molecular gas supply and may be responsible for the eventual quenching of its star formation. The importance of outflows extends beyond individual galaxies to the enrichment of the intergalactic medium. The metals observed in the low-density gas between galaxies, detected through absorption lines in the spectra of background quasars, must have been transported there from galaxies, and galactic outflows are the primary mechanism for this transport. The chemical enrichment of the intergalactic medium is not uniform, but shows correlations with the proximity to galaxies and observations of the circumgalactic medium, the gas within roughly a few hundred kiloparsecs of a galaxy, but outside its main body, reveal a complex multiphase medium that includes both inflowing gas being accreted for the first time and outflowing gas being expelled by feedback processes. Understanding the balance between inflows and outflows, the so-called baryon cycle, is now recognized as central to understanding galaxy evolution, and much observational and theoretical effort is being devoted to characterizing the circumgalactic medium and its role in regulating the gas supply available for star formation. Some galaxies exhibit extreme behavior, not in their luminosity or mass, but in the rapidity or violence of transient events occurring within them. Tidal disruption events, in which a star passing too close to the central supermassive black hole is torn apart by tidal forces, and its debris is accreted over a period of months to years. produce flares that can temporarily make the nucleus of an otherwise quiescent galaxy as bright as an active galactic nucleus. The most extreme tidal disruption events discovered so far have luminosities exceeding 10 to the 45 ergs per second, comparable to the most luminous quasars, but they fade on timescales of months rather than persisting for millions of years. The event AT2021WX, reported in 2023, was initially classified as an extremely luminous transient at a redshift of 0.995, with a peak luminosity of approximately 2 times 10 to the 46 ergs per second, sustained over at least 2 years, making it one of the most energetic events ever recorded. Its interpretation remains debated, with some analyses suggesting it could be an extreme tidal disruption of a massive gas cloud rather than a single star, or possibly a new type of nuclear transient related to changes in the accretion state of the central black hole. Gamma-ray bursts, while typically associated with individual stellar events, such as the collapse of massive stars or the merger of neutron stars, also have implications for the galaxies in which they occur. Long-duration gamma-ray bursts, lasting more than 2 seconds, are associated with the deaths of massive stars and are therefore traces of recent star formation. They tend to occur preferentially in low metallicity galaxies, possibly because the progenitor stars require low metallicity to retain enough angular momentum to produce the relativistic jet that powers the burst. The host galaxies of long gamma-ray bursts are typically small, blue, irregular, and actively star-forming, representing a population that might otherwise be difficult to study at the high redshifts where many bursts are detected. The most distant gamma-ray burst with a secure redshift, GRB 090423, occurred at a redshift of 8.2, corresponding to a time when the universe was only about 600 million years old, and its host galaxy, if it could be detected, would provide information about the conditions of star formation at that early epoch. The topic of extreme galaxies also encompasses objects defined by their unusual morphologies or formation channels. The so-called green pea galaxies, identified serendipitously by citizen scientists in the Galaxy Zoo project, are compact, intensely star-forming galaxies with strong emission lines that give them a distinctive green appearance in the color composites of the Sloan Digital Sky Survey. Their properties, including their compactness, high star formation rates, low metallicities, and high ionization parameters, make them potential local analogues of the galaxies responsible for the reionization of the universe at redshifts above 6. The reionization epoch, during which the intergalactic hydrogen transitioned from a neutral state to the ionized state observed today, is thought to have been driven primarily by ultraviolet radiation from young stars in early galaxies, and understanding which galaxies produced the ionizing photons and how those photons escaped into the intergalactic medium is a major outstanding question. Green pea galaxies have been found to have high escape fractions of ionizing radiation, in some cases exceeding 20%, making them unusual among local galaxies, but potentially representative of the broader galaxy population at high redshift. The Lyman alpha blobs, or LABs, are another class of spatially extended and extreme emission line objects found primarily at redshifts of 2 to 3. These are enormous clouds of hydrogen gas extending over hundreds of kiloparsecs that emit strongly in the Lyman alpha line of hydrogen at 121.6 nanometers in the rest frame. The origin of the Lyman alpha emission is debated, with proposed mechanisms including cooling radiation from gas, accreting onto dark matter halos, scattering of Lyman alpha photons produced by embedded star-forming galaxies or active galactic nuclei, and emission powered by superwind-driven shocks from galaxy-scale outflows. The largest known Lyman alpha blob, LAB-1, in the SSA-22 protocluster at redshift 3.09, extends over roughly 300 kiloparsecs and contains several sub-millimeter bright galaxies within its boundaries. The association of labs with protoclusters suggests that they trace the most massive structures in the process of assembly at cosmic noon, and their study provides a window into the physics of gas accretion and cooling in the most massive halos of the early universe. Some of the most extreme galaxies are extreme precisely because they should not exist, or at least should not exist in the form in which we observe them, according to prevailing theoretical expectations. The discovery of mature disk galaxies at high redshifts, for example, challenges the expectation that disks are fragile structures that are easily disrupted by mergers and should therefore be rare at early epochs when the merger rate was higher. The galaxy Rebels 25, observed by the James Webb Space Telescope at a redshift of approximately 7.3, shows evidence of ordered rotation consistent with a settled disk at an epoch when the universe was only about 700 million years old. If confirmed, this would imply that disk galaxies can form and survive much earlier than many models predicted, potentially requiring revisions to our understanding of the role of mergers in shaping galaxy morphology at high redshift. Similarly, the detection of grand design spiral structure in galaxies at redshifts above 2 has been cited as evidence that the conditions for sustaining spiral density waves can be met much earlier than previously assumed. The concept of cosmic downsizing adds another layer to the discussion of extreme galaxies. Downsizing refers to the observational finding that the most massive galaxies formed their stars earliest and most rapidly, while less massive galaxies continued forming stars over longer periods and to more recent times. This is, at first glance, counterintuitive in a hierarchical cosmology, where the most massive structures are assembled last through the merger of smaller ones. The resolution lies in the distinction between the assembly of dark matter halos, which does proceed hierarchically, and the formation of stars within those halos, which is regulated by the complex interplay of gas cooling, feedback, and environmental processes. The most massive halos at early times are the sites of the most intense star formation, because they contain the most gas and the deepest potential wells, and they quench earliest because their very intensity triggers powerful feedback mechanisms that shut down star formation. Less massive halos, by contrast, form stars more slowly and over longer periods, because their shallower potential wells are less efficient at retaining gas, but also less effective at generating the feedback needed for quenching. The extreme galaxies at high redshift, the sub-millimeter galaxies, the dusty star-forming galaxies, and the massive quiescent galaxies of the early universe are all manifestations of the most massive end of this downsizing trend, and understanding their formation and evolution is essential for understanding how the galaxy population as a whole came to have the properties observed today. The circumgalactic and intergalactic environments of extreme galaxies are themselves subjects of increasing study. The detection of enormous reservoirs of gas around galaxies, revealed through absorption spectroscopy of background sources and through emission in Lyman alpha and other lines, shows that galaxies are not isolated islands of matter, but are connected to their surroundings by flows of gas that regulate their star formation and growth. The concept of cold mode accretion, in which gas flows along the filaments of the cosmic web directly into galaxies without being shock-heated to the virial temperature of the halo, has been proposed as a mechanism for sustaining high star formation rates in massive galaxies at high redshift, and some simulations suggest that this mode of accretion dominates in halos below a critical mass of roughly 10 to the 12 solar masses at redshifts above 2. In more massive halos, the infalling gas is shock-heated to temperatures of millions of Kelvin and must cool radiatively before it can reach the galaxy and fuel star formation, a process that can be suppressed by active galactic nucleus feedback. The transition between these two regimes has implications for the observed properties of galaxies as a function of mass and epoch, and mapping the gas in and around galaxies at different redshifts is a frontier area of observational astrophysics. The extreme galaxies discussed here span an enormous range of properties, from the smallest and faintest ultra-faint dwarfs to the most luminous quasars and hot dogs, from the most dark matter-dominated systems to galaxies apparently devoid of dark matter, from galaxies forming thousands of solar masses of stars per year to those that have formed no new stars in billions of years, from objects at redshifts above 14 to structures in the nearby universe whose properties we can study in exquisite detail. What unites them is not any single physical property, but their position at the tails of the distributions that describe the galaxy population, the regions where the physical processes governing galaxy formation and evolution are pushed to their limits, and where the assumptions and approximations that work well for typical galaxies may break down. Every extreme galaxy is, in a sense, a natural experiment that tests the completeness and correctness of our theoretical understanding, and the history of extragalactic astronomy over the past several decades has been shaped to a significant degree by the discovery of objects that were not anticipated, that challenged existing models, and that motivated the development of new theoretical frameworks and new observational capabilities. The transition from photographic plates to CCDs, from ground-based telescopes to space-based observatories, from single-dish radio telescopes to interferometric arrays, and from optical astronomy to truly multi-wavelength and now multi-messenger observations, has progressively revealed new populations of extreme galaxies that were invisible to earlier generations of instruments. Each new telescope, each new survey, and each new detection method has expanded the known boundaries of the galaxy population and, in doing so, has deepened our understanding of the physical processes that shape the universe on its largest scales. The ongoing and planned observational programs, including continued observations with the James Webb Space Telescope, the upcoming Vera C. Rubin Observatory with its legacy survey of space and time, the Square Kilometre Array and its precursor instruments in radio astronomy, the Euclid Space Mission for wide-field infrared surveys, the Nancy Grace Roman Space Telescope for high-resolution infrared imaging and spectroscopy, and the Extremely Large Telescope and other next-generation ground-based optical infrared telescopes will inevitably discover new galaxies that push the boundaries of what is known and challenge the theoretical models that have been constructed to explain them. The history of the field strongly suggests that the most extreme galaxies of the next decade have not yet been imagined, and that their discovery will, as it has so many times before, force revisions to our understanding that will ripple through astrophysics and cosmology in ways that are difficult to predict from the vantage point of the present. The study of extreme galaxies is not merely a pursuit of cosmic record-keeping, though the records themselves have scientific value as benchmarks against which models must be tested. It is a method of interrogating the physical processes that govern the formation and evolution of all galaxies. By examining the conditions under which those processes produce their most dramatic outcomes, a galaxy forming stars at 4,000 solar masses per year is not just an impressive number. It is a constraint on the efficiency of gas cooling, the availability of molecular hydrogen, the role of turbulence and magnetic fields in regulating fragmentation, the IMF under extreme conditions, and the feedback mechanisms that must eventually halt the starburst. A black hole of 40 billion solar masses is not just a large number, it is a constraint on the growth rate of black holes, the duty cycle of active galactic nuclei, the efficiency of angular momentum transport in accretion flows, and the history of mergers that may have contributed to its assembly. A galaxy with no dark matter is not just a curiosity. It is a test of the fundamental nature of dark matter, the mechanisms by which it can be separated from baryonic matter, and the validity of alternative theories of gravity. In each case, the extreme object sits at the point where theoretical models are most tightly constrained and most vulnerable to falsification. And it is precisely at these points that the most informative confrontations between theory and observation occur. The intellectual framework for understanding extreme galaxies has itself evolved considerably over the decades. The recognition that galaxy properties follow scaling relations, that these relations have scatter, that the scatter has physical meaning, and that the outliers from the relations are often the most physically interesting objects, has transformed the field from one focused primarily on classification and morphology to one focused on the underlying physics of galaxy formation. The advent of large statistical surveys, beginning with the Sloan Digital Sky Survey in the early 2000s and continuing with its successors, has made it possible to define the typical properties of galaxies with unprecedented precision, and therefore to identify the extremes with greater confidence. At the same time, advances in computational astrophysics have made it possible to simulate the formation of galaxies from cosmological initial conditions with increasing realism, and these simulations provide the theoretical benchmarks against which the observed extremes can be compared. When observed extremes fall outside the range predicted by simulations, it indicates either that the simulations are missing important physics, that the observational measurements are affected by systematic errors, or that the objects in question are genuinely rare events in the tails of the distributions, requiring larger simulation volumes to capture. Distinguishing among these possibilities is a central challenge of the field, and one that requires the close integration of observational and theoretical efforts. The narrative of extreme galaxies is ultimately a narrative about the limits of physical processes in the cosmos. The maximum rates at which gas can cool, stars can form, and black holes can grow. The minimum amounts of dark matter that can host a visible galaxy. The earliest times at which massive structures can assemble, and the most violent interactions that gravity and hydrodynamics can produce. These limits are set not by any single physical law, but by the complex interplay of gravity, thermodynamics, nuclear physics, magnetohydrodynamics, and radiative transfer operating across scales from individual stars to the cosmic web. Understanding where these limits lie, why they lie where they do, and what happens when they are approached is one of the deepest and most enduring goals of astrophysics. And the extreme galaxies we have found, along with those we have yet to discover, are among the most powerful tools we have for pursuing it.